exhaust is fucking come on brand new, huh?
Yeah.
The purpose of this is to add more seat pressure to the ball and force more oil. Well, prevent oil from escaping through the jets and therefore force more onto the rotor bearings. Drop the ball. Premature wear of the rotor bearings. So by doing this, you guarantee that there will be more seat pressure at the ball, and that will prevent the ball from lifting prematurely. And again, it's the RPM of the engine that gets the weight of the ball to lift up against the spring pressure. So it will actually begin to spray later when boost is actually coming in.
When you say spray, where it's spraying it into that bearing, or?
Well,
the
yes,
rotor?
exactly. Oil pressure comes in to the crankshaft through the rear side plate at the rear stationary gear and through the front stationary gear, and they meet in the cavity in the center of the shaft, and then it gets directed to the bearings and the stationary gear bearings, but it also gets directed to the oil jets, which essentially spray oil under pressure into the backside of the rotors to keep them cool. If it was a very high output motor, that hole in that metering jet is 2.5 millimeters. If it was a very high output motor, then we'd open that up to 3 millimeters. Again, with two springs, it would delay the opening point, and then when it actually opened up, it would spray a heavier amount of oil into the rotor to cool it. Yeah, at this point we're going to start assembling the engine. So the rotors have been assembled from some time back. Nothing really special about this motor. We're not shooting for extreme amount of power, but it is going to be a very properly built motor. The only real modifications that we have done to the rotors is basically clearance them, as all turbocharged engines should be clearanced, and properly balanced with the proprietary counterweight for the that we designed to use the RX8 front cover with the 3rd generation block. Aside from that, the rotors are low compression from an 87 turbo engine, which will allow us to run a lot of boost. But you know, there's no, it's not scalloped, lightened, any of those other modifications that you would do to a full race engine. This is going to be just a very properly done street engine that will sustain 400 horsepower with, you know, absolutely no issues. All the seals have been loaded. The apex seals are in place. Notice that I have a number on each corner, 4, 5, and 6. Here is the front rotor, 1, 2, and 3. The reason for that is because the corners of the apex seals have been adjusted for maximum sealing to the main beam of the seal. They all vary slightly, so they've been selectively fitted so that we have maximum compression and don't have to worry about letting the engine break in and have the seals wear into the housings. Same thing with the housings. You know, these are all used parts. There's nothing brand new about this engine because we're trying to do it to prove a concept, and we're using good second-hand parts. The truck weight surface has been polished and ground. The exhaust ports are basically stock timing, but contoured properly. They're both identical. Actually, these are actually non-turbo housings, which had the noise reduction exhaust insert. So we milled them out in the mill, and you can see the modifications there to allow the flow necessary for a turbo engine, and at the same time, we went ahead and polished them and just brought them up to standards for what a turbo port should look like. In essence, even though the port timing is exactly as stock, in the process of taking out the noise reduction inserts, gone ahead and opened up the very top edges of the port just a little bit more. So area-wise, even though the timing is opening and closing points are identical, area-wise, it's been increased by probably an additional 20%.
You've also done the cooling mods to the...
Yes, this housing has all the, well, again, going back to the beginning, as far as the idea is to build a solid motor, we went ahead and did the cooling modifications that we normally do to our racing engines, and take every precaution and every effort possible to have the engine run as cool as possible and be as reliable as possible, given the power that we intend to extract from it. And the cooler, as everybody knows, heat is the #1 enemy to a rotary engine. So we're going to do every effort to make sure that this thing runs dead cold. Important, very mildly. The exhausts are slightly larger. Again, the idea is to have a solid motor and not affect the idle quality in any way, shape, or form. We can always crank up more boost, and that's the idea. Is the engine is built to take a lot of boost, even though it's not a race-oriented engine. With the low compression rotors, high quality seals, selectively fitted, street ported to a relatively mild state, high quality pieces, should make a very solid motor. At this point, what I intend to do is basically load up the water compression and water seals, and then we're going to spray graphite on the rotors, the bearings, and the side housings. It's something that we do on every engine, and at the same time reduce the braking period. So we're going to be doing that, and then once everything is coated, we'll actually stack it up.
Quick question for people that want to buy kits from us with the motors already included in it. What do you recommend? That they get a JDM motor from one of these import companies, or buy the parts from you, like we're doing here?
Well,
these parts.
Obviously, my inventory of parts is limited. Yes, we build a lot of engines, and through the years I've acquired some inventory. But if a customer wants us to build them an engine, either they will need to provide a JDM core or pay for us to find a JDM core. Very lucky in the neighborhood. One is a block away, and another one's within 3 miles. We have 2 importers of Japanese engines, Japanese domestic market engines. That's where the term JDM comes from. So I do have a good supply of parts, whether it's for my own inventory or we have to go get them. What I do keep a massive amount of inventory are low compression rotors. 3rd generation rotors are poor. They don't take much boost. They actually implode under mild boost per se. The compression is rather high for a turbo engine. Not quite as high as the RX8, but the RX8 engines for turbocharging, it's like not what you want to do. It's not a matter of when they're going to fail, it's a matter that they will fail. The rotors are crap, the compression is extremely high, the side seals with that wedge shape have a tendency to stick. The engine's just not friendly for turbocharging, even though a lot of people have, tried with very poor results. Everybody claims it's huge numbers, but when the push comes to shove, they can't back them up. So, and again, it's those engines they're nuclear reactors as far as heat, generate so much heat that they're prone to fail. They're prone to melt the O-rings, both the compression and the water seals. Even in stock form after X amount of miles. So imagine when you put a turbo on them and you get more power and you get more heat. Let go.
So just so we have an idea, ballpark figures, what does the average JDM motor go for? And then on top of that, what would you recommend as far as the machining, and what would that cost, and the low compression rotors and so forth?
Well, that all depends on what the customer wants and what power target he is looking for. JDM third generation engines can be had anywhere from, I would say, $1,300 to $1,800, depending on who the supplier is and what relationship you have with that particular person. I mean, I've paid as little as $1,000 for them, complete engines. I paid as much as $1,500, depending on their stock. Sometimes they have them, sometimes they don't. Obviously supply and demand. If the guy only has 2 left, he's going to try to get as much money as he can out of them. But even a bone stock third generation engine, bone stock, you put it in with the proper counterweight and the proper integration of this kit, between what we will provide and the cost of the JDM engine will actually be, if it's bone stock, will actually cost less than a rebuild of an RX8 engine. So if the customer wants a built motor with a specific horsepower target, then obviously that's going to get into higher and higher levels of performance and also cost. On the high end, an engine block built by us that will support daily 600 horsepower. For the block alone, you're looking at about $9,800. Block alone. That doesn't include intake, exhaust, turbo, water pump. Block alone. That would be with a motor that's balanced, low compression, lightened rotors, scallop, you name it, basically a full race engine without a dry sump system. And somewhere in the middle, people may not necessarily want to go so far. We've made motors that have made much more than that with other proprietary technology as for port timing and progressive intake, opening. There's a lot of technology that will go into a full race turbo racing engine that's not necessary for the street. But regardless, the engine has to be able to take the power. So the idea always with a built motor, turbo motor, is to build it to its maximum capacity and only use 60 or 70% out of it. Then if you really want to get crazy and go all out, then you've got the motor already, that can handle it. It's so easy to get huge power out of bolt-ons without actually building the engine that people get carried away and blow them up. You know, it doesn't matter whether it's a rotary engine or a piston engine or Toyota or Chevrolet or whatever. You know, those 2JZ super engines, those things are monsters. They make stupid power. But they gotta be built. You know, with bolt-ons, you can only take it up to a certain level. Beyond that point, the internals will let go. Same thing with rotary engine. You know, you have different year eccentric shafts are stronger than others. You have different year rotors that are different in compression, also are stronger than others. There's just a lot of attention to what the final product that you're looking for has to be, and basically it's a custom built engine, not just a stock motor. Give me 1 second, I'm going to show you what happens to third generation rotors when you boost them up above 1 bar, which is 15 pounds. A very common problem with third generation REW and Cosmo rotors. They implode like that, which basically what that means is that and this happens at about 15-16 pounds of boost. The temperature in the combustion chamber is such that the material is so thin that it can't take the combustion pressure, and they implode. And this one I keep here to show people, but I've actually seen them look at that one. Seen them to the point where they'll actually crack and blow compression into the crankcase and blow all the oil right out of the filler and the dipstick. So anyone who thinks that they can build a 500 horsepower engine on pump gas using 93 rotors is dreaming. Yeah, you can do it, and it's gonna last you know, a day or two. When you finally get it tuned and you start abusing it, this is the end result. So again, going back to this engine here, this is an engine that is built solid. Take punishment, take boost, not crazy in poor timing, not crazy in building an ultra lightweight rotating assembly. The idea here is to have a very solid daily driver with, you know, 380, 400 horsepower on tap.
The question I was trying to get posed to you was what would the likely cost be, for example, to use these type of low compression rotors with a JDM block, for example, and then you've got the rebuild kit, right? You put all new apex seals, that kind of stuff in, and the water seals and everything, or? Well,
everything adds up, you know. A properly done low compression rotating assembly, whether from us or from Racing Beat, is going to be somewhere in the neighborhood of about $2,400. That includes both rotors, both counterweights, balanced. And on top of that, you know, if you go ahead and you lighten them and do scallops and things of that nature, that adds more cost to it. For this particular project, it's going to require the proprietary RX8 rotor. Now, if we build the engine, a proprietary RX8 counterweight to work with a third-gen engine. If we build the engine with the intentions of building one of these cars, then obviously we'll go ahead and make the counterweight and put it into when we balance the engine, put it into the engine block at no cost, extra cost to the customer, because it's part of balancing. So whether I balance an engine with you know, a 93 front counterweight or a 89 front counterweight, or the counterweights that we're actually using for these modifications, which are actually old school 12A counterweights, highly modified, you know, if I'm building you a built motor that's balanced for this project, it will have the right counterweight. Okay. If you're looking at doing this the cheapest way possible, okay? You get yourself a bone stock JDM third generation REW engine that is known to be good, especially if you can get it out of a running car. It's gonna be even better. Okay, take the front cover off. Put in our front counterweight and our rear counterweight because they're going to be balanced as a unit for that engine. And put in the RX8 front cover, stick it in the car, and get rid of the twin turbos that they come with, and put in a single turbo, you know, anything that'll do the job. GT35, a whole set, 60-1, whatever. There's a zillion turbos out there right now that will sustain that kind of power. You're gonna make 350, 360 horse. That's twice what the RX8 is doing. And it's gonna cost you less than to rebuild an RX8 engine. That's it. Simple. Conversely, if you want to build an engine and make more power, then obviously that's a different scenario. But if you want to, if the customer wants to do this as cheap as possible, you take a third gen engine block, put in the pieces that will supply with the kit, and bolt it in, and you're done. Obviously, one of the main components of the skid is the electronic computer that is plug and play from the RX8. Without that, this kit would not be feasible, because that computer, along with main piggyback, which will basically take over the controls of the engine, ignition, fuel, and the ECU of the car continues to run the rest of the functions: fly-by-wire throttle, oil meter and pump, air conditioner, power steering, all that stuff. The minute that you remove or alter, like most people do, then you give up all those features, and now the car is, you know, toy and not, you know, a nice cruiser, totally functional RX8. That was the whole gamut, the whole idea about doing this kit this way, is so that every single feature of the car still works as it came from the factory, with twice the power.
So the idea is you can get away with doing it cheap, but then if you want to bump the boost up into anything over 1 bar, now you're looking at building an engine. So it's smarter, or in the long run cheaper perhaps, to do all that up front while the engine's out of the car, because then you're guaranteed new seals, new apex seals. You can go with the low compression rotors off the bat, and you can still run it at 350, 380 horsepower until other parts of the whole drivetrain let go, like the transmission you talked about earlier. Can't really sustain over 380 horsepower. So when that lets go, you would probably go with an RX-7 transmission, and then you could bump the boost up to whatever.
Exactly. Well, the RX-7 transmissions have been known to handle 550 horsepower to the wheels reliably, not much more than that. And recently I've learned that the Gen 2 RX8 transmission is far more powerful than the Gen 1 transmission.
And those will swap?
Yeah, they'll be a direct swap out. Just take one and everything. Switch without any adaptions. You know? But yes, I mean, there's quite a few ways of going about doing this. But even if you were to do it at this cheapest level with a third gen motor, you guarantee you're going to have twice the power.
Now you usually only put the high-low bar in certain segments of the...
Yes, around the vicinity of the spark plugs, and the vicinity of the exhaust port. On the compression seal, go all the way around from the dowel pin, upper dowel pin, to the exhaust port. And then I also, where the O-ring comes together, I also put some Hylamar right there. On the water seal, around the exhaust port and around the spark plugs. The rest of it I use Vaseline.
What's the reason for that again?
This Hylamar is fairly expensive, and I use it in the parts of the engine that are known to run hotter than the other parts of the engine. So just to ensure more life out of the seal. It's really not necessary to put it all over the engine. Also, wherever there are O-rings, it's also a good idea to use it. It's an anaerobic sealant that stays tacky until the absence of oxygen. That's when it actually seals. The rest of the engine runs relatively cool. There's hot zones and cold zones, and in the cold zones, you know, just Vaseline is more than sufficient. It's how I built all the engines all my life, and I mean, you know, we built some $50,000 engines, we built some $90,000 four-rotor engines, and they all get the exact same treatment as far as the sealants go. There's no real advantage to running the Hylamar all the way around the motor. If there was, I'd be doing it. We would have known about it already, because I've been doing this for a long time, going on 30 years. So in that period of time, we built quite a few of them. Vaseline has many which is the orange one, and it has a union right there. So that union goes in right by this bolt. That's where it's recommended. You can put it anywhere, but it's recommended to put it there because that is the coldest section of the engine, and you want to have that union where one of the tension bolts is located, because even though the engine is, you know, theoretically compresses evenly, you may have a little more grip by where that bolt is at. These O-rings have a black side and a white side. There's no real reason why it is that way, except to visually inform the builder that he got the seal twisted. It can easily happen. So the idea is so that once you put the seal in place, the black goes up, you don't see, like for instance, if it's relatively easy to do that. Twist the seal, build the engine, and you end up leaking water. So the whole purpose of having the color is just an indication to the builder that the seal is twisted. And it's relatively easy to do. It happens, I've seen it happen a lot. Everybody's human, everybody can make a mistake. It provides a very sleek, very smooth surface in which to have full lubrication at startup before oil actually gets through the engine, and it also accelerates the braking process. We put this on bearings, on any working surface. Shoot a light film and get a matte gray finish to it. It doesn't matter if it gets on the seals. We also got this in app, right? I'll get it on the bearing also. Evenly all the way around. Spray both sides of the rotor, spray the housing, spray the bearing, and spray the crank. And like I said before, this film stays, impregnates itself into the metal, and we've done taking apart races that engines that have raced for 24 hours at Daytona, and the graphite is still on the shaft. Okay. So now it's time for the rotor housing, and then the corners to the apexes. That is repeated between, when I'm doing machine work. I don't have to set the machine, one way or another for every single operation. Otherwise, it takes forever. As it is. Everybody says that I take forever.
Oh, sorry. Oh, shit. Sorry, man.
Okay, Chris, get okay. Housing, slide in, fast. Did a hell of a job with the epoxy and filing them down, but it's very time consuming. Very time consuming. So you can see we put the graphite on the truckhood surface also. Again, it provides instant lubrication and at the same time accelerates the braking process.
That gasket maker you put on the housing there, that was just over some of the repairs, or?
Yeah, over some of the repairs. Just to, well, actually it's on this side. Just precautionary. Didn't really need it, but why not?
Set it right here on that little table.
Just a rubber band to hold the seals in place. All right. That's it. Now, go ahead and you see how the silicone, that low viscosity silicone squeezes right out. So I don't have to worry about having to torque it and this and that at this point.
Now with that graphite spray, what is your break-in time now on the motors?
Well, you should still, the longer you give it as far as braking time, the better, the longer the engine's going to run. Braking time is really, really, really important. It's essential. But some people just go out there and beat on it from the get-go. You know? Especially the drag racing guys. The drag racing guys don't have the opportunity or the luxury to give it a braking period. So they need to build in excessive clearances from the get-go because they don't have the luxury of being able to give the engine proper braking period. And most of those guys don't even just build them and go out and race. They don't even break them in on the dyno. They use the dyno for tuning purposes, and once they have a tune, just build engines and go beat on them.
Now what do you recommend for a braking time then?
I'd like to see about at least 1,000, 1,200 miles. The first 500 below 5,000 RPM, and then every 1,000 RPM, another 100, 150 miles on top of that, so that by the time that you are at 1,000 miles, you can turn the engine 9,000 plus. Okay, at this point, basically we got to put the corners into the apex seals. So, as I mentioned before, I have every apex seal has been selectively fitted with its own corner. So now I got to clean off some of the graphite to see which one goes where. Now that one I can see it's number 3. This is number 2, and this is number 1. But just in case, I'm going to go ahead and make sure that I clean it off, just so that we don't screw up. Alright. Now I need some super glue.
Right there.
Is it open already? I'm gonna have one. And I really could use that fan right there. Put a little dab of super glue just to keep the corner in place. I'm going to be very careful to catch the spring in the right location. Sometimes you can get the spring in between the main beam of the apex seal in the corner and not know it, and torque the motor down, and the motor will at best lock up. And if it doesn't, you fire it up and destroy the side housings in no time. The reason why I'm holding it is just so that the super glue will actually stick. Hold it for about 20-30 seconds and good to go. Okay, that's number 1. I don't know if you noticed, but before I did this, I actually took a little toothpick and
Cleaned
took
out
out
the-
all the grease.
Yeah. You glue these in place just to keep them in position when you put the next housing on it? Or?
Yeah, exactly. Because they're spring loaded, they have a tendency to pop. And if you know, when you're putting that center housing, the center intermediate, that's really the most critical point of the whole build, because you have to pull the shaft out up, rotate the rotor, kind of wiggle the intermediate housing in place, and it's easy for these little guys to pop out. So rather than take that chance, I'll just glue them in place, and you know, it's just a safety margin. It actually has an adverse effect at startup, because the seal will actually, the super glue will hold the seal from snapping out. And as the engine rotates and it crosses the minor axis, the seals have a tendency to be driven into the groove. And the engines are harder to start. Can catch you by surprise. But I built quite enough of these to know that that's an issue.
So it's harder to start initially. You
Yes.
use an ATF to break it loose or something?
Exactly. Okay. Now at this point, we have to rotate the rotor, and this is at this point. This is the step that they'll have a tendency to pop out. Well, you see, the super glue
It's
glued in. So I'm gonna take a flywheel and put it in there. It to like the 2 o'clock position, otherwise it doesn't allow you to get that intermediate housing in place. That's the point that if they're gonna pop, they'll pop out. Okay.
I don't remember which one we mapped.
I had a million of these,
I know.
and I don't know how. Like I said, this is the real critical part of building the engine. And a lot of mistakes are made at this point.
Why'd you put that stick under there?
That stick pulls the shaft up, and because the shaft has to come up in order to be able to get that intermediate plate to go like this. You know, you notice that the shaft is, the eccentric lobes of the shaft are 180 degrees apart. So that intermediate plate has to come off center and go like this, and then go like that, and then be able to fall on the 2 valves. Making sure that I have the correct center housing. When they're all painted, they're all ported. They all look the same.
Yes, it is. Make sure you have the right one.
This is very tricky. See here how it has to twist and then straighten out and then fall on the pins. So that's really the purpose of that little stick. Pulls the shaft up, allows me to do that. Now at this point, something that I always do, because it happened to me one time, and it happened on one of my angles. At this point, I'm going to make sure that those little corners are all in place. This. See how easy the housing drops when you pull the shaft out? Most people will have to have somebody help them out, hold the shaft, this and that. Now that the center housing is in place, this should have really been done before. I'm going to spray the lobe and the stationary gear section of the shaft. And same thing with the rotor. We want to spray the rotor bearing on the sides. The back side first. It's the side that's going to go down. You have to wait for it to dry. When it dries, it gets that flat black, very opaque look to it. That's when it's cured. It's what I've always done, and it works perfect. I do it on all my race engines. We have race engines that spin at 10,400 RPM, and they live 3 seasons, and this is what I use. As soon as oil begins to is pumped and begins to travel through all of its passages, it will push the grease right out. But in the meantime, the grease is heavy in viscosity, so prevents any metal-to-metal contact while there is prior to having oil pressure.
Yeah.
Right. Move the rubber band up that holds the apex seals in place, so that when we drop the rotor housing, it doesn't, the corner of the seal won't pinch the housing. The housings are very soft, they're made out of aluminum and very easy to distort. These O-rings seal the housing because that's the main oil gallery to the upper dowel pin. If those O-rings were not there, the engine would leak oil. It's very important that they're in and properly replaced.
You don't have to put this on both surfaces, do you?
No.
Just one.
Be really, really, really careful with that top O-ring. This is very easy to pinch it. I'm gonna push this down a little bit more so that I can get more of the rotor housing down. Okay, now at this point, we've got more than 3/4 of the apex seal in place, covered by the rotor housing, so
There you go.
that's it. assembly grease out of the corner seals so that the super glue will take, which is about halfway down the corner seal. Again, just like before, corners are numbered. So, see how the silicone will squeeze out?
Right.
A lot of lack of measuring. That's really what brings most of the mistakes. There's so much to measure in these engines.
Thousandths of an inch too, right?
Yeah, you know, distortion, rotor housing distortion. A lot of it could be fixed, but it requires measurement upon measurements, you know. Another big mistake that people make is not getting the side seal to corner seal clearance correct, and the engines lose compression like that. Using again, a huge problem, using brand new apex seals on used rotor housings. The rotor housings, as they wear, will, if you magnify it, that this flat surface will actually develop scratches, hills and valleys. And you put a brand new, perfectly flat apex seal, it'll ride on the top of the creases of those hills and valleys and lose compression across the bottom. That's such a common mistake. There's nothing wrong with using good used rotor housings that are serviceable, but as you saw with at the beginning, you know, we have a process to get them dead smooth, clean, and true, and it's done by different grades of sanding and sanding paper and actual grinding.
You're talking about the surface of the rotor housing?
Yes, exactly. And you know, you got clearance issues, you know, rotor bearings, stationary gear bearings, all that has to be measured. Everything, you know, there's different thicknesses of bearings for different applications. So there's a lot of areas to make mistakes. It just comes from lack of experience. Lines here. I basically go from the top of the exhaust port all the way around the blowdown area throughout the spark plug area and right to here. On the water seal, again, from the dowel pin where the spark plugs are up to about here, and then on the exhaust port from about the dowel to about the top of the exhaust port. Those are the really hot areas of the engine. The rest of the engine block itself is relatively cool. Now we're not going to torque fully the engine down right now. So I'm just putting some bolts through it. So I need to wash the rest of the through bolts. Hey Ed. Where did you have all those Here we go.
Sounds like it's making compression.
Huh?
It sounds like it's making some compression. You know, the corner seals are probably still stuck, right?
Mm-hmm. Smells good. And there we have it. Next step is put the oil pump, the counterweights, all that stuff in front. Seal it with the RX8 front cover. Put on our clutch package, oil pan. We'll have it in the car by next weekend.